Welcome to Kwara State University. This is Physics Department and I'm taking Physics 102. My name is Adegbenro Ajani and today we'll be dealing with topics that deals with current electricity. I believe this is week 3 according to our calendar, and I'll be the one to be taking the following course outlines. We'll be dealing with electric current, conservation of charges, Coulomb's law, electric field lines, potential, electric field potential, then electric current, Ohm's law, resistivity, and electric power. I'll be putting us through those topics today, and I believe we'll have a good time together. So please stay back and let's have some discussion. Physics 102, and today is 30th 05 2023. Alright, so the first thing we deal with is current electricity, but before that we have to talk about the types of electricity. We have two types of electricity. We have the current electricity and we have the static electricity. So let's start dealing with static electricity as a matter of introduction. So let's see, what is static electricity? Current electricity means when the electric charge is in motion, but static electricity means the electric charge is at rest. So, and among the effects due to static electricity are plastic rubbed on hair. When you rub a plastic on your hair, it will attract some piece of paper. Then the plastic is negatively charged, your hair is positively charged. Then of course, the paper is positively charged. So when you pick it, the negative will attract the positive. Then we have a wooden jumper worn over a nylon blouse, gives sparks when taken off. A piece of polythene rubber rubbed with a duster will attract small pieces of paper. Then the balloon rubbed in the jumper will often stick to the wall. Then collection of dust on the television screen. So those are the effects of motionless electricities that we can see, and it has some applications. What are the uses of static electricity? The first one is electric spray. Then the other one is garden spray, and the third one is electrostatic dust collectors in chimneys. So we have the origin of this static electricity. It started in 600 BC and it was discovered by the Greek philosophers. Now, the Greek people discovered that the silk clothes they wear attract or get sparked during their dry season. So they call that spark, or they call that electrons or charge, they call it amber according to their language. So the word for electricity itself comes from the Greek word amber, which means electron. So in 1729, Gray found that static electricity could be discharged from an object through the human body, thus giving the idea of conductors and insulator. And of course, conductors allow free passage of electricity, while insulator does not. So in an uncharged or natural body, the number of electrons is equal to the number of proton, and this is why we said an electron or an atom is electronically or electrically neutral, because the number of electron is equal to the number of proton in an atom when is not excited at an unexcited state. So in conductors, free electrons are not strongly attached to an atom and are thus free to move about from one atom to another. An example of these conductors are silver, zinc, copper, aluminium, etc. Iron. Then insulators have their electrons strongly bound to atoms and hence cannot move from one atom to the other. An example of insulator, we have plastic, we have wood, we have quartz, we have silk, we have so many other things. So in 1945, Dufay discovered that there were two types of static charge. He called one positive, he called the other one negative, and this was later confirmed by Benjamin Franklin. When we are charging a body, we charge a body by friction. That's when we're dealing with static electricity. When two substances as glass and silk are rubbed together, they become electrically charged. Thus, rubbing some electrons are transferred from the glass to the silk. So the silk acquires a net negative charge, that's excess electrons, while the glass acquires a net positive charge as electron deficit. So if ebonite rod is rubbed with 4, the ebonite is negatively charged and the 4 is positively charged. And this is what we can see according to the diagram here. Let's quickly discuss the Coulomb's law. The Coulomb's law. The Coulomb's law says that if two isolated point charges Q1 and Q2 separated by a distance r, the magnitude of the force of attraction or repulsion between them is given as F, which is equal to Q1 Q2 over r square. So what he's saying, if we have the force of attraction or repulsion, that's one thing about Coulomb's law. It's different from gravitational law. Gravitational force talks about force of attraction only, while Coulomb's law talks about force of attraction and repulsion. And it says is equal to K Q1 Q2 divided by r square, where K is a constant, is equal to 1 over 4 pi epsilon 4 pi E naught. So that's what our K is, and it has a function of 9 times 10 raised to power 9. That's the value of K that we have. So with this, E now is the permittivity of free space, which is equal to 8.85 times 10 to the power minus 12 Coulomb square per Newton per meter squared. Then we have the electronic charge is equal to 1.6 exponential 19. So we have value for electronic charge, or we call it Q, is equal to 1.6 times 10 to the power minus 19 coulombs. So we have to take note of all these values while we are doing some basic calculations. So I want you to come along as we move on this. So from here we move on to electric field. What is electric field? Electric field of a charge Q is the region of space over which the force due to the charge can be experienced. Then we have electric field intensity. Electric field intensity, an electric field is present at a point if a force of electrostatic origin acts on a charge placed at that point. So electric field intensity E at that point is defined as the force per unit charge at that point. So which is equal to E, which is electric field intensity, which is equal to F divided by Q. So E is a vector quantity. When you see this side, it's talking about a vector quantity. The sign up here is equal to force, then divided by Q. And the unit of force is Newton. The unit of Q is Coulomb. So the unit for electric field intensity is Newton per Coulomb, or you have Newton per Coulomb, as we see it there. As we can see there. So then we move on to electric line of force. An electric line of force indicates the direction of the force on a positive charge placed in an electric field. It is also the direction of the electric field intensity at that point. Lines of force are always directed away from a positive charge and directed towards a negative charge. This is what we have here. So when we are dealing with a line of force, it moves away from a negative charge. So if you have a positive charge here, you have a negative charge here. So it moves away from a positive charge, then it moves towards the negative charge. So that's what we have. That's what we have here, and we can have this line of force operating together. So in other words, it can move away from here. You have this, how it moves. The line of force can move like this. They are imaginary lines, so in most cases they use dotted line for them. Dotted line. Oh, sorry, I wanted to pick. Okay, so they use dotted line, because they tends to be imaginary lines. Okay, and we have like this. So it's moving away from here. You can see it's moving away from here, then it's entering here. So they are entering into the negative. They are moving away from the positive. They are entering into, that's if they are not isolated. But if they are isolated, you have something like, sorry, let me break this one, because I said they are imaginary lines. So they are imaginary lines. They are not. Okay. So if they are isolated charges, so you have your plus, then you have your minus. So it moves towards the minus. Okay. You have the charge, the point, the lines moving towards, they're moving away from the plus. It's moving away. So you must take note of that, because that could be an objective question telling you the direction of the line of force on a body. I want us to solve few problems from here. Let's see this question. This one says calculate the electrostatic force between two electrons separated by a distance of 10 to power minus 10. Now 10 to power minus 10 is called 1 angstroms. Angstrom is 10 to power minus 10, and this is the unit for angstrom, is capital letter A, putting 0 on top. And is equal to 10 to power minus 10 meters. Okay, because if they give you 10 angstroms, you must know how to convert it to meters. So the question says calculate the electrostatic force between two electrons separated by a distance of 1 angstroms, 1 angstrom. Then they give us electronic charge of 1.6 raised to power minus 19 coulombs. So this is what we do by our formula. Remember that we said that force is equal to K Q1 Q2 divided by R squared. If you are still following, then definitely we are given our Q1 and then we are given our Q2. So Q1 and Q2 are the same because it's talking about electronic charge. So quickly bring that out. That means you have your K, which is equal to 9 10 to the power what 9. Then your Q1, which is equal to Q2. Okay, Q1, sorry, Q1 is equal to Q2, then which is equal to 1.6. That's electronic charge exponential minus 19 coulombs. So then we are given your R. They give you R to be equal to 10 to power minus 10, meters. So they said it's separated by a distance of that. So what we do from here is that your F now is equal to, what is your K? 9 times 10 to the power 9 multiplied by 1.6, that's one of the charges, times 10 to the power 9 minus 19 times the second charge Q2, 1.6 10 to the power minus 19, then divided by 10 to the power minus 10, that's your separation squared. So if you do this well, you should be able to get 23.04. So try that on your own and let's see what you will get. Times 10 to the power minus 9 Newton. Minus 9 Newton. That's what I have from here. So try that from your own hand and let's see what you will get. You will get from there. So I want us to see another problem, if we can quickly run through it. Let's see this. This one says it says a charge of magnitude 2 exponential minus 4 coulombs experiences a turn is talking about a force, okay, of 80 Newton in an electric field. So find the electric field intensity of this field. Of course, this is also very simple. We come to our blank sheet. So remember we said electric field the other time is equal to force over charge, which is coulombs. So, and that was what we said at that time. So from here we are asked to calculate find the electric field. We are given a charge. So the charge given, Q, was given to be 2 times 10 to the power minus 4 coulombs. Minus 4 coulombs. Then we are given force to be 80 Newton. F is equal to 80 Newton. I believe we are okay with that, as simple as it could be. So our E now is going to be equal to, what is our force? 80 divided by 2 times 10 to the power minus 4. So which is equal to 40 times 10 raised to power 4 Newton per coulomb. That's the unit. The unit is Newton per coulomb. Or we can say that E is equal to 4, then multiply by 10 to the power 5. If instead of 40, we take 10 from it, then Newton per coulomb. So that's what we have on that. So I want us to go to other subheadings. Let's see what is called Gauss's law. Have you heard Gauss's law before? All right, let's see Gauss's law. Now, Gauss's law is very useful for some of you that will be in engineering. You will make use of this law when you are dealing with flow, when you are dealing with Maxwell equation, when you are dealing with Poisson and equation of continuity. It's very important. It's one of the Maxwell equations, but Poisson law deals directly with electric charge, or with charge of a particle. So it states that, Gauss's law states that the total flux through a closed surface is equal to the net charge enclosed by the surface divided by the permittivity of free space, epsilon naught. So he said the total flux, so to paraphrase, so Gauss's law says, he said the total flux, that's your summation, okay? The total flux, so that's the summation of your flux, so is equal to, the summation of your flux is equal to your net charge. So he's saying, he's saying if this is your flux, that's phi, okay, is equal to epsilon Q, that's your charge. That's what he's saying. The total flux is equal to the charge. That's what Gauss's law. It also says that the algebraic sum of all charges enclosed within that surface, the algebraic sum, is also equal to the algebraic sum of all the forces enclosed between that surface. This means that if a surface encloses a pair of equal but opposite charges, the net force is equal to 0. So Gauss's law of electrostatic provides the relation between the electric field and the electric charge that produce it. So that's all about Gauss's law. I believe you can just have that at the part of your mind, because of some of you that will deal with it in the future. So you won't say you have never heard of it before. All right. So let's talk about electric potential. Electric potential. Now, the potential at a point is defined as the energy transformed in bringing a unit positive charge from infinity to that point against the action of the field. So for a sphere of radius r carrying a charge q, the potential at its surface is given by V, which is equal to 1 over 4 pi E Q over R. So definitely your potential is V. We call potential, we use V for potential. So V is equal to Q divided by 4 pi, this is pi E R. So that's what it's saying. That's your electric potential. That's what it is. So the units are volts, or we use joule per coulombs. We use joule per coulombs. We can say volts or joule per coulomb. That's the unit of, because we are talking about work done here in bringing a body into into a point from the infinity. So, and we say unlike force and electric field, which are vector quantity, of course, electric potential is a scalar quantity. Hence, when calculating V, the sign on the charges are considered. So the work done in moving a charge Q between 2 points which have different potential is equal to work done, which is equal to QV. So don't forget this formula as well. Work done is equal to QV, which is equal to we have charge multiplied by the potential. That's what our work done is. In the uniform electric field of intensity E, the potential difference between 2 points distance apart is equal to V, which is equal to ED. So we also have this formula also, that E is equal to V over D. So also have this at the back of your mind, that electric field is equal to electric potential divided by the distance, or the interval between them. All right, so let's see some problems as well, so that we can move on quickly to some other areas. This problem talk is, calculate the electric potential at a point P with distance of 1 meter from either two charges of 10 microcoulombs and minus 5 microcoulombs, which are 10 centimeters apart. Calculate also the potential energy of a charge plus 2 microcoulombs placed at point P. So take note of that question while we go ahead to crack it. All right. Solution now. So the question says, calculate the electric field. The first thing is learn how to draw. You must learn how to interpret all this in the drawing. So let the point P at 1 meter from 10 centimeter charge. So the first thing is, let us draw. What is it saying? We have this. This is 0.1 meters. This is the separation between those two charges. This one is plus. You take it to this side, microcoulombs. Then you have minus 5 microcoulombs. So we have that. Then we have a point P. A point P is here. Okay, so we call it P. This is a point P here. So that means we have, and they said the distance with this point, this is an imaginary line, is 1 meters. So then definitely we don't know this hypotenuse. So we find it. So let's call this R2. Okay, and of course the R2, by geometry, is equal to square root of 1 squared plus 0.1 squared. That's this line plus this line, the square of the two. So definitely that's what we have from there. Then potential at P. So potential at P due to plus 10 microcoulomb charge. So it's given as, let's call that V1, which is equal to K Q1 divided by, this is K now, divided by R1. Okay, K Q1, this is Q1. So definitely this is equal to so V now, V1 now. So put the value of K there, 9 times 10 to the power 9 multiplied by, what is our Q1? We've been given Q1, which is 10 microcoulombs. So we take it to microcoulombs, which is 10 to the power minus 6. 10 times 10 to the power minus 6. That is in microcoulombs. Then we have divided by 1.0. So which is equal to 90 times 10 to the power 3. This is what I get. Calculate your own. So joule. Then we also do for the potential at P due to the second charge minus 5 microcoulombs now. So we have, let's call that V2 now, which is equal to V2, which is potential at P due to minus 5 microcoulombs, which is equal to KQ2 divided by R2. And definitely we have V2 is equal to 9 times 10 to the power 9 multiplied by, so we have 5 times 10 to the power minus 6, then divided by 1.0. So definitely we have, for here we have 45 times 10 to the power 3 joule. That's what we have at this point. So, but I think we are carrying minus from here. Our charge is minus, so everything we get here becomes minus. So it's going to be like that. All right. So the potential at P now. Potential at P is the algebraic sum of V1 and V2. Potential at P is the algebraic sum of of V1 and V2. So we have the two potentials together. So when we have the two together, so it will be 990 times 10 raised to power, I think we have 3. So because we are adding, and that this one is carrying minus before, we have minus here, so we just add that minus with it, 45 exponential what now 3. So everything is in joule. So then definitely we have the answer we have is going to be 45 times 10 raised to power. So we have 45 times 10 raised to power 3. That's the answer we have. So in volts, volt, then which is also equal to 4.5, I think, times 10 raised to power 4 in volts. So that's what we have from there. So taking note of this, the second question says, the question goes further and it says, calculate also the potential energy of a +2 microcoulombs charge placed at point P. So we have to do that also. So in doing this, the potential energy of +2 microcoulombs charge placed at P is given as, so we are dealing with potential energy now. So placing +2 microcoulombs charge at P. So we have energy or work done, which is going to be what? QV. And we have our Q. Our Q, they give us to be 2, that's +2. That's times to our -6. That's our charge. Then multiply that by what is our V now? The V that we have been able to get, which is 4.5 times 10 raised to power 4.5 times 10 raised to power 4 volts. So our work done now is going to be equal to 0.09 joule. That's our work done. So that's the answer for that question. So I want us to see another question on this before we move on to other related problem. Let's see this problem. This one says A potential difference of 3.6 volts is maintained between two plates which are 20 centimeters apart. Calculate the electric field intensity between the plates. So this will be like problem number 5 or 6 that we shall be solving now. So we said a potential difference solution. Potential difference of so we have V to be equal to 3.6 volts. Okay, then it's maintained between two plates which are so our D now, or A, D is equal to, which is separation, 20 centimeters, of course, which is equal to 20 times 10 to the power minus 2 meters. So you take that to meters apart. Calculate the electric field intensity between the plates, and we know that V is equal to, E is equal to V over D. I told you this formula the other time, and I said you should not forget it. So definitely this is going to be 3.6 volts divided by 20 exponential minus 2, and I believe you should be able to get 16.0. Is it 16 now or 18.0? 18.0. Please do your calculation yourself. Volts per meter. So you should be able to get that one. So I want us to move to the last segment of the course, which is electric current. Electric current, the path followed by the flow of electric current is called a circuit. So circuit is the path flow followed by electric current. So this has to be closed. You have to close a circuit. A complete circuit carrying a steady current must contain a source of EMF, electromotive force, which drives charge out of the source from the negative terminal to that of a positive terminal. So it moves from negative to positive. Mostly the source of EMF is a battery, which is a term used for collection of cells. So a battery contains two or more cells. A cell is a single it's a single source of EMF, and the EMF is electromotive force, and it is defined as the voltage of a battery when the battery is not in use, when the battery is in position, or some textbook will tell you when the circuit is open, when the battery is not connected. So we have combination of cells. So this sketch, this table shows us the combination of cell, the series combination, and the parallel combination of cell. You can see how this is put. We have cell 1, E1, E2, E3. Those are the cell. Then we have, when they are connected in parallel, E1, E2, E3. Those are the cells there. Then from these, we have positive 1 is connected to the negative 1. That's when we are dealing with cells in parallel. Okay, when we are dealing with cells in series, you connect just connect the terminals together. The positive is connected to the negative, connected to the positive, connected to the negative. So that's what you do for those ones in series. And when you are doing for that of in parallel, you connect all the positive together, then connect all the negative together, and now combine them at the end of the day. So please don't forget that. That's very important. So the EMF of a battery is equal to the sum of the EMFs of the individual cells. That's for EMF in series. Then the EMF of the battery is equal to the EMF of each separate cells at any moment. That's for EMF in parallel. Then we have some other things like that. So please put those ones to heart. Let's deal with Ohm's law now. Ohm's law, the current through a metallic conductor is directly proportional to the potential difference across its end, provided the temperature and other physical factors are constant. So this law applies to metals and some alloys, and are called ohmic conductors. So we have ohmic and non-ohmic conductor. Ohmic conductors are the conductors that obey Ohm's law, while non-ohmic conductors are the conductors that do not obey Ohm's law. Example of conductors that obey Ohm's laws, they are our normal conductors, the conducting wire, the Constantine wire, some of these conductors. But those ones that do not obey Ohm's law, they are diodes, they are these varactors, they are these diodes, they are some of these semiconductor materials that do not obey Ohm's law. They do not obey. The graph is not a straight line graph like that of a high V graph that we know. So Constantine wire is ohmic conductor, semiconductors, valves, and transistor. Mathematically, it can be expressed as V is equal to IR. For a conductor of length L, cross-sectional area A, the resistance of the material is given as R, which is equal to rho which is equal to rho L over area. So this is where we begin to put notice on some of this equation. So the first thing we have to note is that current passing through a metallic conductor, that's Ohm's law. Ohm's law says that V, voltage, is equal to I R. This R is a constant, that's the resistance of a wire, and then we now say that R now is equal to rho L over R is equal to rho L. This is rho now, rho L over area. So definitely we can make rho subject of our formula, where rho now is equal to RA over L. So this rho is what we call resistivity. Rho is resistivity of the material, and we should not forget it. So the resistivity has the opposite. We also have some other parameters like conductance. What is a conductance? Conductance is denoted by G. This one is rho. Okay, resistivity is rho. Now G now, which is equal to 1 over resistance. So it is inverse of our resistance, that's our conductance, or inverse of the voltage. So those are little things I believe we need to know from those ends. So then we have let's quickly run through this. It says generally the resistance of all substances changes to some degree with changes in temperature in the case of pure metals and most metallic alloys. The resistance increases with a rise in temperature. Carbon, semiconductors, non-metals, and many electrolyte solutions show a decrease in resistance as their temperature is raised. So special alloys, for example, contains, Constantine, also called Eureka, and manganese show very slight changes in the resistance over a large range of temperature. Hence, for practical purpose, the resistance of these alloys are considered independent of temperature. So for temperature ranges that are not too great, this variation may be represented approximately as RT, total resistance, is equal to R naught into bracket 1 plus alpha, which is coefficient of your resistance, then to bracket T, change in temperature, T minus T naught, then bracket close. And this is also, that means our T now, we can make T subject of the formula, which is equal to RT minus R naught divided by R100 minus R naught multiplied by 100, where RT is the resistance at temperature T, and then R naught is the resistance at temperature, initial temperature. Then R100 is the resistance at temperature 100, and then alpha is the temperature coefficient of the resistance. So let's solve these two problems as we begin to call it a day. The first one says a copper wire has a resistance of 10 raised to power of 10.0 ohms at 20 degrees Celsius. They say what will be its resistivity at 80 degrees Celsius, and at 0 degrees Celsius the temperature coefficient of resistance of the copper is 0.0004 per degree Celsius. So that's what the question says. Let's try to crack this out here. Let me get a new page for this. Okay, and then this. All right, so we start from this. So the first one, solution now. So the first one, so we have R, our R, which is equal to 10.0 ohms, ohms, then, and change in temperature, our delta T, is equal to 80 minus 20 as we have been given there, which is equal to 60 degree Celsius. 60 degrees Celsius. So that's our change in resistance. So and the resistance, at 80 degrees will be R plus delta R, which is equal to 12 points. This is going to be equal to 12 point. So okay, let's do this first. Let's try and do. Let's do this. Let's do this delta R first. Delta R, which is equal to alpha, like the formula I just gave you, delta T. Okay, so which is equal to what is our alpha? 0.000. We are given in the question, multiplied by what is our R? So 10.0 ohms. That's our R. Then multiply by what is our delta T, 60. This is what we have here, 60 degrees that we have here. If you do this, so you have 2.4 ohms that you have. So if you had this 2.4, so that means the resistance at 80 degrees now. So the resistance at 80 degrees, which is what we have here now. So at 80 degrees, it will be equal to 12.4 ohms, because it will be 10 plus 2.4 that we have up there. So that's resistance at 80 degrees. Then resistance at minus 20 degrees now. So question 2, second question. So at minus delta T, which is going to be minus 20 degrees, that's our second question. So it will be the same way we follow delta R, which is equal to alpha R delta T. So this will be what is our alpha? 0.0004 multiplied by 10.0, then multiplied by minus 20 degrees Celsius, 20 degrees Celsius. So if you do this, you should have minus 0.8 ohms. This is what you have here. So the resistance now, the R at 0 degrees now, so will be R plus delta R, which is what we have from there, and then which is going to be, what is our R? 10.0 ohms plus into bracket minus 0.8, then you will have 9.2 ohms. So that's what we have for that question. Let's take the last question for the day as we have our break for the week. All right, this one says a platinum wire 80 centimeter long is to have a resistance of 0.1 ohms. What should its diameter be? The resistivity of platinum is 1.1 exponential minus 7 ohm meter. So we have been given that. So we come to our sheet now. All right, let me get a new page, please. Okay. So said the platinum wire of, now don't forget that we said resistance is equal to rho L. I think we wrote this together the other time, divided by area. That's what we said. And when we are dealing with wire, so that means the area of a wire is going to be rho L divided by pi r squared. So don't forget that. And then of course, which is also equal to 4 rho L divided by pi d squared. So don't forget all those ones. But let's deal with R now. So that means our R is equal to, now when you make from here, from this place, make R subject of your formula. When you make R subject of your formula, you have R, which is equal to square root of rho L divided by pi R. So try that yourself and see what you will get. So definitely our R now is going to be equal to square root of, what is our rho L? Rho is equal to 1.1 as it has been given, exponential minus 7, then multiply by 0.8, then divided by pi. Of course we know pi, multiply by 0.1. So pi is 22 over 7 or 3.142, which is going to be equal to 5.3 exponential minus 4. That's it for minus 4 meters. So this is what we have here. And let me get one more page. Okay. So this is what we have here. Then definitely that means our R now is equal to 0.53 millimeters. So if we take what we have in meters to millimeter, we have this. Then our diameter D now is equal to 2R, which is equal to 0.53 times 2. Then we're going to have 1.06 millimeter. That's what we have at the end of the day. So we'll see you next week, and then the next person to take you is Dr. Adegbenro, by the grace of God. God bless you all, and bye bye. So please, if you have any question, you can channel it through our group. Send your question through the groups. If you have any anything to say, please send it there, and I will give you an assignment which I will also send to the group at the end of the day. Thank you, and bye for now.